In this video, we're going to discuss the concepts of voltage, current, electrical resistance, and use it from an object and system perspective. We're going to be doing what seems to be quite a lot, but it's not as much as it will look like. We're going to define terms such as open circuit, closed circuit, voltage, also known as an EMF. We're also going to be looking at electrical current, defining electrical resistance and resistivity, also the terms ohmic and non-ohmic. We're also going to differentiate between the different types of electrical circuits, understand the difference between electrical resistance and resistivity, and begin to look at the relationships between voltage and electrical current, as well as electrical resistance. Again, this sounds like a whole lot. It really isn't going to be that much, and this is a concepts that we're going to be working out throughout the entire year. So we're just introducing these topics. Why are we doing this? Because electricity is nearly in everything that we do. We live in an electronic digital age. Everything runs off electricity. And many people actually have a very weak understanding on what electricity is, or even the basic concepts behind it. Also, since we don't see electrical charges, many people will find this concept of electricity very confusing when we have very little time at the end of the year to look at it. So if we start now and work throughout the entire year, we'll be able to build up a very strong foundation and understanding of electricity so that when you really need to understand these topics, it'll be very intuitive to you. So let's first take a look at the term circuit. A circuit really is nothing more than a route that something takes from one place to the other. For example, a racing circuit is just the racetrack that a car will travel. An electrical circuit is the path that charges will travel from start to finish. So it's kind of always a closed loop. So if we take a look at our electrical circuit, we see just like the racing circuit, it really is just a circuit where you can think of the positive side of the battery as the starting line. The current travels up, around, back, and returns the battery on the negative side. It's like how a car will actually start on one side of the track, run all the way through the track, and return to where it started from. That's what makes it a racing circuit. Now let's talk about the terms open and closed circuits. These are the scientific and technical terms for a circuit that is on or off. We focus on the switch. If the switch is in a closed position, which means electricity can flow through the circuit is on, and we call it a closed circuit. However, if there is a detachment where the circuit isn't touching, where the switch isn't touching the opposite side of the circuit, it's considered an open circuit, and so that is an off circuit. Many people will try to describe a switch as a door. It's actually a really bad way of viewing it because for people to flow through a doorway, you need to have the door open rather than closed. But if you think of it as some sort of creature that travels through the wall and then it comes to a door jamb, it can't travel through the doorway unless the door is closed because electricity travels through the wall, not through the open space. So a closed circuit is always on and a open circuit is always off. If you notice, a lot of times you see a power button that's a circle with a line through it. It actually isn't a circle with a line through it. You have an open circle, which means off, and then that line is actually a collapsed or closed circle, which means on. So that switch actually means open circuit or closed circuit rather than on or off. Throughout the year, we're going to see how circuits come in a variety of different formats. There are actually three that we're going to look at throughout the year. The first one is called a series circuit. This is the classic line of winter or Christmas lights that you see where they're all in one common string. If we take a look at a single wire, we see a single light bulb, I should say, we see a single wire going in and a single wire going out. This means that if one light goes out, the rest of the lights all go out because each light serves as its own personal electrical switch. And if there's a break in the light bulb, then there is no way for electricity to travel through the circuit. The circuit is now an open circuit rather than a closed circuit. And if you have any experience with these lights, you see this from time to time where all of a sudden you plug them in, one light, the lights don't light up, and you become very frustrated because now you have to go through all the lights looking for the one light that's broken. Replace that one light, and all of a sudden they all light up. So for a series circuit, everyone is connected directly towards one another. The electricity that flows through one is the electricity that flows through all. And if one does not work, they all do not work. However, there's also another arrangement of lights that we often see called a parallel circuit. If you notice the wires here, you'll see that they are thicker, and you'll actually notice that there is a recess inside. That's because that's not one electrical wire, it's actually two. You have a positive side that goes on one part of the light bulb, and you have a negative side that goes on the other side of the light bulb. This means that each light bulb is in itself directly connected to the light bulb directly. So we can see that this light bulb is connected directly this way, and this light bulb is directly this way. When this happens, we call these parallel circuits. Now, not parallel because geometrically they look parallel. In fact, we look at these lights, they don't really look very parallel at all. It's just the fact that everyone is connected directly to the power source. These require much more wire, and they also consume energy much faster. The series circuit is simpler to make, but they have the downside of when one goes out, they all go out. In a parallel circuit, if this guy goes out, the other light bulb, which is still connected directly to the battery, stays on. Most of your house lights are arranged this way so that when one light goes out, everything else still stays on, and you know to replace that one light bulb rather than trying to go through all of your light bulbs in a dark house because one light bulb isn't working, stopping all the other lights from working. In a series circuit, you really only need one switch to control everything, because if this switch is open, then no electricity can travel through the switch, so no electricity can travel through any of the light bulbs, because there's only one path for the electricity to travel. In the parallel circuit, however, you need multiple switches to control everything. Each light bulb or device needs its own particular power switch, and a lot of times you'll have one master switch that controls everything. So this is often called a master switch, which will turn everything on or everything off. Please notice the master switch is actually in series with the battery, while all of the regular switches for each item are actually in series with the item that they're attached to. But every item is parallel with each other. So if I turn this switch off, this item can still run as long as this switch is in the on position or closed position. Our power strips are a wonderful example of a parallel circuit. Here I have the master switch that can turn everything on or off. Then all of my plugs are parallel to one another. This is why I can have my computer plugged in one outlet, my cell phone plugged into another outlet, and a desk lamp for another outlet. And if my lamp is turned off, my other two things can operate. The easiest analogy I can think of to help understand how electricity works in a circuit is to actually think of things as a factory shipping products off to various businesses. The factory is like the battery, and the items are the energy. The businesses are going to be our lights or resistors or whatever it is that we're going to use. So these could be lights or electrical motors or whatever it is that we're going to be using. Now, As a factory, I want to ship my product, in this case energy, to the various businesses, which would be the individual lights or resistors or motors or whatever that's in the circuit. So if we understand how factories ship goods, then we understand how circuits operate. And we can at least visualize a factory shipping items out rather than viewing charges. So that's what we're going to focus on, something we can physically see. So we're going to be focusing on a factory shipping items. Now, as a factory, I need some mechanism or delivery device to get my products to the different factories. One item is I could use a single individual, such as a bike messenger, to carry the item on their back. This is a single charge for the circuit. This is our fundamental charge. This would be like our protons or our electrons. And these small electrons are the ones that physically move throughout the wires. So that is what I could possibly use. It's the smallest increment I can use because I cannot cut a person in half. That is illegal, and try to have them ship packages out. That would not work. So we are going to have a whole person ship this out, and that would be our fundamental particle. The problem is if I have a massive quantity of charges or product to be sent out, I can't have all these bike messengers. I need a larger delivery device. So a lot of times we'll use a delivery truck. And a truck is an equivalent to many people on a bike. So a truck is called a coulomb of charge, and 1 coulomb of charge is the equivalent to a whole load of bike messengers. In fact, 1 coulomb of charge is equivalent to 6.25 times 10 to the 18 fundamental charges. That means it's 6.25 times 10 to the 18 electrons to make up 1 coulomb, or 6.25 times 10 to the positive 18 protons to make a coulomb of charge. Just to get a real idea of how big that number truly is, I have it written out here where you can see all those zeros. Please notice this is way bigger than 1,000, a million, a billion. It's even bigger than a trillion. So this is a number that makes very little sense to us on a everyday scale because we never deal with anything this large or this numerous. And one of the problems we have with large numbers is we have no idea what they mean because we've never seen a quantity that large before. Now, while it's true if I have a single truck or coulomb of charge, I can get a fair amount of packages through. But if I'm going to really run a very successful business, I need a fleet of trucks. I need several trucks moving down the roadway at any given time. The roadway would be the wire of the circuit. So a lot of times we describe electrical current as the flow of charges, which would be the number of coulombs that flow by in a second. It's really the amount of traffic that's flowing through on my roadway. We define traffic rate as the number of cars or trucks that pass through a given point in a given time frame. For us, electrical current will be the number of charges or coulombs that flow through a point, such as this line, in a second. The symbol that we use for electrical current is the letter I. You may complain, I always do. It doesn't make any sense on why we use letter I, because if you take a look at how we spell current, even I don't spell current with the letter I. And you have by now noticed how well I can spell. All right, a coulomb, current is often measured as coulomb per second. That's also known as an ampere or amps. So when you see a battery that has a rating of 200 cranking amps or a fuse that's a 5 amp fuse, they're talking about the amount of current the battery can produce or the amount of current you can have flow through that fuse before it burns out. Here we have a couple of practice questions we're going to try out real fast. So what I want you to do is try to pause the video, try to answer the question, and then play the video to see how you have done. So in this first question, we have a wire that has 800 coulombs of charge flowing through it in 5 seconds. What is, and ignore the fact there's a question mark there because that's bad grammar. That should be a period. What is the electrical current flowing through the wire? So again, just simply pause the video. Once you're ready, play the video and you can see how you solve this question. Okay, I'm going to show the answer in 3, 2, 1. So since current is the number of coulombs you have per second, 800 coulombs flow by in 5 seconds. So 800 divided by 5 is 160 coulombs per second, or 160 amps. The next question, there's a battery that produces 4 amps. That's going to be the amount of electrical current. So how much time does it take for 8 coulombs of charge to flow out of the battery? Once again, pause the video. Once you think you have an answer, play the video and you can see if you're right. All right, I'm going to show the answer in 3. Okay, so I'm going to show the answer in 3, 2, 1. So we know current, again, is going to be the number of coulombs per second, or charge over time. So my time would be my coulombs, or charge, over my current. So 8 coulombs over 4 amps is 2 seconds. Because remember, an amp is a coulomb per second. My last question, there is an ammeter that measures the current flowing through a wire. The meter measures 2 amps. How much charge flows through the meter in 1 minute? So again, pause the video once you think you have an answer, play the video, and see if you got it correct. Okay, so I'm going to show this in 3, 2, 1. So we know current, again, was the number of charges or coulombs per time, or seconds. So I can manipulate this to say coulombs is current times time. But you have to be careful of the units. And amp is a coulomb per second. So I can't use 1 minute. I must convert 1 minute into 60 seconds. So 2 coulombs per second times 60 seconds is 120 coulombs, not 2, which some people come up with because they didn't convert the units properly. So always make sure your time is in seconds when working with amps, and you'll never have an issue. So again, if we have my electrical circuit, which is a lot like a factory delivering goods to a business, my battery is the factory where it carries these goods, and my trucks are the fleet that's going to carry the goods out to my businesses. Now, a couple of quick things about this. The first thing is, when I have trucks leave the factory, I want the same number of trucks returning. The only difference is when the trucks leave the factory, they are packed with the boxes, which means the charges have a lot of energy. The same number of charges return to the factory, just like the trucks do. I don't want to lose trucks. The only difference is the charges that return don't have energy, just like the trucks, come back without any boxes. So charges will always be conserved. This means if I have a current here of, let's say, 8 amps flowing through and 2 amps flow through this business, then I must have 2 amps and 2 amps because it's like 8 trucks coming down the line, and 2 trucks go to this road going to business 1. So that means 2 trucks, the same 2 trucks go to business 2, and those same 2 trucks return. But if 2 trucks are going through business 1 and 2, how many trucks go through business 3? Well, that has to be 6 amps because 8 trucks will be split up between 2 and 6, and I will have a total of 8 trucks return. So in short, circuits consume or use up electrical energy, which would be the boxes in the trucks, never the electrical charges, never using up the trucks. In chemistry, you learned something called conservation of charge. That's exactly what this is. No one item ever uses up charges. They only use up the energy that the charges carry and deliver to them. You can also think of it in terms of biology real fast. Your oxygen is like the energy, and your red blood cells is that what carries the nutrients and the energy to your other cells. you don't actually use up the red blood cells. The red blood cells flow through the body. It's only the material that they carry that is used up and consumed by the rest of the body. Now let's talk about the concept of electrical potential. Electrical potential is a concept that people often find confusing because we attribute it to energy. In fact, in one of your earlier grades, you might have learned something called potential energy. And that is something that we will be looking at later on in the course as well. However, electrical potential isn't potential energy because it's not even called energy. It's actually in the name that this is not energy, but it is related to energy. If we consider a box that a factory is going to ship off as a unit of energy, that would be the joule that we're all used to working with. My factory doesn't ship a box, it ships many boxes. And it's not convenient to actually try and discuss my shipment in terms of individual boxes, but as groups. That's where electric potential comes in. Electric potential is the energy that's carried by 1 coulomb of charge. It's like the number of boxes that are carried by a single truckload. That is what we're going to be discussing here. The symbol that we use for electric potential is the capital letter V, named after Nikola Volta, and the unit that we use a lot of times to describe voltage is actually called a volt. But a single volt is actually a joule per coulomb. Just like it would be the number of packages per truck, energy would be, the volt would be a joule energy per coulomb, energy per charge. One of the things that people really get confused with on electric potential is the term voltage, because that's something we always hear people talk about. I've got the voltage of a battery is 10 volts or 9 volts. My motor requires 13 volts of battery. You need 12 volts to start your car. But no one ever talks about electric potential. And that's because electric potential doesn't have a lot of meaning. It's only how it changes that matters. So for example, my business, when energy comes through, we're interested not in how many boxes are being delivered to the business on the truck, if the truck's going to go to other businesses. We're interested in how many packages the business takes in. So if you notice, the truck comes in with all these packages, but when it leaves, it has less packages. The difference in the amount of packages is the voltage. It's the difference in the electric potential that is across the resistor. It's the amount of electric potential that the item uses up. So voltage is often known as a potential difference. It's the potential that you have here minus the potential that you have here. So the symbol that we use for voltage is delta V. It's actually going to be the voltage final leaving minus voltage initial. So this really equals V final minus V initial. The triangle, or the delta symbol, means change. It always means a subtraction of final minus initial. Again, one of the things that confuses people is the units. The units for volts is, the units for voltage is volts. The unit for electric potential is volts. And that's because a voltage is just the change in the electric potential. So here we have a couple of practice problems on the concept of voltage. Just try to solve them through. Again, just like before, I'm going to pause the video so you can do the work on your own and you can see how you did on them. So for the first question, I have an electric motor that absorbs 700 joules of energy from 2 coulombs of charge. I simply want to calculate the voltage of the motor. So this absorbed 700 joules, which was being delivered by 2 coulombs of charge. So I just simply want to find that voltage. Okay, so I'm going to show the answer in 3, 2, 1. So, since voltage is the energy I receive per charge, 700 joules in 2 coulombs is 350 350 joules per coulomb, or 350 volts for short. My next question, there is an electrical light that receives 20 volts from a battery while having 3 coulombs of charge flow through it. How much energy did the light bulb receive? So again, pause the video real fast, try and solve this out, and then you can see how you did. Show, I'll show the answer in 3, 2, 1. So my voltage is energy per charge. So I could easily find my energy by saying voltage times charge. So 20 volts times 3 coulombs is 60 joules. An easy trick for a lot of this stuff is you could actually just replace the volts with a joule per coulomb. And that makes things a whole lot easier because 20 joules per coulomb times 3 coulombs would be 60 joules. My last question, there's a resistor that receives a voltage of 10 volts. Pretend that's an I, that should be an I. So if the charges that leave the battery have an electric potential of 24 volts, what is the electric potential of the charges that enter the resistor? Okay, so we're going to go over this question in 3, 2, 1. You can actually think of this kind of like our whole package thing. If I have a business that receives 10 boxes and the truck drives away from the business with 24 boxes, the question is, how many boxes were in the truck to begin with? And the answer really is 34 boxes. My voltage, 10 volts, is equal to the change in the potential, electric potential. Now, a lot of people will ask the following, well, if it's off by 10, how do I know it's not 14? Which is a great question. But think of it from a logic standpoint. If I have 14 boxes coming into a business and I drop off 10 boxes, I can't have 24 boxes left. I can only have 4 boxes. So I have to have 10 more than 24 because I'm leaving with 24 and I'm dropping off 10. So just more from a logic standpoint. So I can turn around here and say that 34 volts is my starting potential. So in terms of voltage in a circuit, if I have 100 boxes that leave a factory and they all return, then the boxes that travel through business 3 must drop off 100 boxes because they have to come back empty. However, the boxes that travel through business 1 and 2 cannot give each business 100 each. They only carry 100 on their own. So if business 1 takes in 20 boxes, then business 2 must be taking in 80 boxes to equal the 100. If, for example, business 1 though was taking 60 boxes, then business 2 could not take 80 possibly. It would only be able to take in 40. The bottom line is these two amounts here always have to add up to what the factory is offering. So we're going to see the same thing with voltage because the energy has to be conserved. So when the charges go through the circuit, if there's only one resistor or light bulb, it receives the full voltage or the full energy of the battery. However, if I have multiple items along the one route, then that energy or the voltage has to be shared among the individuals until they add up to the total that the battery is offering. So here I have a circuit. This is a very complicated type circuit. However, we should be able to figure out finding the current for each of the missing pieces and the voltage for the following things. So here I have a battery. The symbol that we use for a battery is two parallel lines, one side representing the positive side, one side representing the negative side. The long side is the positive, short side is the negative. We get more into that later on, so don't stress on that. I do not know the voltage of the battery, but I do know that 8 amps leave the battery. 8 amps go down this wire here, where it's going to split up among these resistors. Here I have a resistor whose resistance I do not know, and here's a resistor where I know next to nothing about. And then I have another resistor down here that I know very little about, except it receives 30 volts. And I have to try and figure out now the voltage of the battery, the currents that are flowing into the battery, and over here in this resistor, as well as the current flowing through this resistor. And I need to find out what the voltage of this resistor over here is. And we haven't done a whole lot, so this is something that can appear to be very confusing and overwhelming. And that's fine. But the truth is we already know everything that we need to just by using our business model. The bottom line is 8 trucks are leaving, 8 amps. So 8 trucks are leaving every second, if you will. They're traveling down this line and 6 go this way. Well, out of 8, 6 go along this line. How many have to go this way? And that would be 2 amps, because the amperages have to add up to the total. So this must be 2 amps coming in, and we're not going to destroy trucks. We're not going to lose charges. So 2 amps have to be leaving out. If 6 amps are flowing into this resistor up here, then 6 amps again must be flowing out. And 6 amps must be flowing over here. And 2 amps must be flowing over here. And when my fleet of 6 meets my other fleet of 2, I get a fleet of 8 trucks. And so the returning current is 8 amps. Because again, conservation of charge, conservation of trucks. We're not sacrificing any of our carriers. We want them to leave and return safe. So my currents all add up. Life is good. Now let's take a look at voltages. This one guy got 30 volts. All of that comes from the battery. So what must the voltage of the battery be? It has to be 30. Because this resistor down here gets everything the battery has to offer in a single shipment. So that's going to be 30. Likewise, 30 are on the shipment that comes through this line. If this first resistor takes 18, then the other resistor here must be getting 30 minus 18 volts. So 30 volts minus 18 volts. And so 30 minus 18 is 12. So this must be 12 volts. Looks like a circuit that can be very overwhelming, but we're just using simple conservation principles. Voltages always have to add up to the batteries, and the currents always have to add up to one another as well. So this is what we're going to work on. Again, we really need to have you guys understand this. I would say somewhere in March. So we start now, and believe me, with a very little practice, you're going to have a great handle on this type of work. Now let's talk about how fast the currents flow out of the battery. That is called our current, and the rate at which the current flows depends on 2 things, really. The amount of voltage or energy you have, and the amount of resistance that the roadway puts up to receive that energy. A guy named Ohm came up with a relationship between current and voltage, and saw that in many cases you have a linear relationship. We call this Ohm's law, and he had found that your current is proportional to your voltage. And so he wrote out an equation that said that your voltage was equal to your current times your resistance. So my resistance here is the inverse of my slope. So my slope here is 1 over my resistance. If I make the graph voltage over current, then the slope is equal to my resistance. Basically, the bigger the resistance, the harder it is to get charges to flow through. You can think of it like trucks going through a nice smooth road would have low resistance. Trucks going through a single lane rocky road, that would be something that has a lot of resistance. It'd be very hard to get your charges through there, or your traffic, or your cars through it. So higher slopes mean higher resistance. Lower slopes have lower resistance if I'm graphing things as voltage versus voltage versus current. Do be careful of your graphs. Notice on what is your y-axis, what is your x-axis. If we have reversed the axes, where this is current versus electric potential or voltage, then the lower slope would actually have the higher resistance, and the larger and the lower slope would have the higher resistance, and the larger slope would actually have the lower resistance. This type of graph is very rarely written. The voltage versus current is more practical, but if you're taking the AP test, they can easily go current versus voltage just because they know most people are used to this graph, and so it lays in for an easy trap. So just be aware of that. Resistance is always defined as your voltage across something divided by the current flowing through it. Okay, so again, that, like I said, that was Ohm's law. It's a very simple equation, and this is a base equation. You do not need to memorize this. This is a given equation at all times. You do have to be careful, though, with who writes the equation. I write the equation properly where you have a delta V in there because it's the change in your electric potential. That's the true symbol for voltage. Some websites, some tutors and places like that, they'll just go V equals IR because it's easier. Be careful, that is going to be very misleading because voltage is a change in 2 points, not a single value. It seems like a simple mistake and something that can be easily overlooked and something that does not matter, but it is a huge critical mistake, especially when you're dealing with higher end stuff that we're going to be working with, where you will get confused if you're dealing with voltage or electric potential. So always play it safe, always put the delta V there for voltage, and you will never go wrong. Now, we've already talked about Newton's second law a little bit, and we're now looking at Ohm's law. And one of the problems that people have with physics is they think everything is so different that you have to have all the stuff memorized. The truth is there are a lot of commonalities, and Ohm's law is sometimes known as Newton's second law, but of electricity. And if we take a look at these two laws, we see that there are some commonalities between them. Your voltage actually acts like a force on the charges trying to get them to move. In fact, a lot of times, this is called an EMF, or electromotive force. It's the driving force that makes charges move through a circuit, while delta F is just the net force that we just push or pull on solid objects that we see everywhere. Your current is the change in the charge's behavior. It's the charges that flow through a wire. It's the rate at which they flow. Acceleration is the rate at which an object's motion or behavior changes. So current and acceleration are not the same thing, but again, they are rates of change, and they are driven by this force or voltage, aka electromotive force. Mass is an object's ability to resist a force. Resistance, electrical resistance, is an object's ability to resist a voltage. Physical mass, inertial mass, tries to resist acceleration. Electrical resistance tries to resist electrical current. So again, it's easy to think these two things are very different, but if you see the commonalities and if you have a better handle on forces, you can use that to help yourself understand electricity. And we will generally understand forces better than electricity because we feel forces, we experience forces, and we live with Newton's second law. We do not live with the voltage and Ohm's laws. We utilize it, but we don't actually deal with it because we are not electrical charges. If I wanted to understand which object would have a higher resistance or make it harder for electricity to flow through, one of the things I'd have to compare is the type of material it's made of. So example, simple question, which would be harder for electricity to travel through? This piece of copper or this piece of wood, given that they are the same width and the same length. And most of us know it would be harder for the wood to travel, be harder for electricity to travel through the wood than the copper. That's why we don't make wires made out of wood, we make them out of metal. So wood offers a higher resistivity than metal does if it has the same dimensions. Likewise, if I asked which one of these devices, the copper or wood, will offer a greater electrical resistance, here's a little hard to say. I know metal conducts better than wood, but the metal here is really thin and very long, while the wood is actually thin and very wide. It's actually possible for the wood to actually have less resistance than the copper does, even though the wood naturally is a worse conductor than copper. So electrical resistance is more than just what makes you up. We can think of it as the following. We have two people and one person is just genetically in tune with being a fast track star. Okay, we're talking body weight ratio is ideal. Their leg length is just phenomenal. Their muscle mass is just so in tune. And then we have this other person who's just everyday average non-athletic person type. And the question is, if we were to have them train for a year, who would win in a race? It's easy to turn around and say that the first guy, the one with a genetic disposition for athletics, would in fact be the better runner. But it's more involved than that, really. Because if this person has all the genetic inclinations, but they don't train at all, and the person who is just everyday, not athletic person, who you could consider has pretty much no gift whatsoever for the sport, trains 5 hours a day, 7 days a week, then they are going to be the superior athlete in the end. Same thing with our resistance. Copper, genetically, if you will, has a better disposition to conduct electricity than wood. But there's more involved than just what you're made out of. It's how are you built? What are you doing? How are you shaped? That's going to play a role. So electrical resistance is your overall resistance to slow down charges. It has many different factors. Something called electrical resistivity is just your disposition. The higher the resistivity, the more inclined you are not to let charges flow through. And yes, if I have someone with a genetic disposition for a sport and someone who doesn't, and they train equally hard for equal lengths of time, then the person with the genetic disposition is going to be just the one who's the far superior athlete. However, the true athlete is determined not by their genetics, but by genetics, training, mental mindset, and all the other factors that get played in. Resistance is the final athlete that we see. It is going to depend on your material that makes you up, your resistivity. It's also going to depend on your length and your cross-sectional area. The wider the space, the easier it is for charges to flow through. It's like having a road with many different lanes versus a single lane road. And the longer the path, the more charges are in your way, the harder it is to get everything to be pushed through. So my electrical resistance depends on resistivity, length, and cross-sectional area. Again, you don't need to understand all this stuff right now. You just need to really know that resistivity and resistance are two different things. Resistivity is just a disposition. It doesn't determine solely if you're going to be a good resistor or not. If my voltage and current keep a constant ratio, we call that ohmic. It follows Ohm's law. So delta V equals IR. My resistance is constant. Most of our electrical equipment, such as resistors that we see right here, something that we're going to work on or with, is going to be ohmic. However, not everything follows this rule. Some things go through huge temperature changes. If they go through huge temperature changes, they actually affect the resistivity of the material that makes them up. Light bulbs, for example, are a wonderful example of something that is non-ohmic. If you were to measure the resistance of a light bulb turned off, it's only around 3 ohms. Ohms being the unit for resistance. It's very small. However, when you turn on the light, it can exceed over 400 ohms. And that's because the light bulb gets really, really hot. In fact, the filament of a light bulb is not solid. It's actually a molten metal once it glows. So we see something that follows a non-linear path. So this is something that is called non-ohmic. We cannot use Ohm's law to predict what the current or voltage is going to be. Ohm's law does work for each individual point, so I could still use Ohm's law to find the resistance at this point, and I could use the Ohm's law to find the resistance at this point, but the resistances at these 2 points are not the same. The slopes will be different because the ratios are different. All right, so that's going to pretty much wrap us up here. I know this sounds like a lot. We are going to be working on this stuff all the way through, and we're going to take it step by step. So come to class with questions. We're going to take this throughout the week, and we're going to work on this throughout the school year. So I'll see you guys in class, and enjoy the rest of your evening.